freaked me out. Yeah, so an eigenvalue cannot overpull its weight. So if the eigenvalue only has a weight of 1, then I better only get one free variable here. And if I get more than that, then I need to go back and check my work again. I must have a mistake. Okay, now we do know that we can cross off a row, for sure. Does anybody have a preference about crossing off a row right now? The last row? Okay. I'm fine with that. I'm going to cross off the last row. And then the other 2 rows, what I'm going to do, and you guys can be quick with your EROs, but I'm going to, first of all, wipe off all the minus signs. Okay, and then I'm also, notice every single number is even. Let me just make everything like, let me divide through by 2, just to make everything a nice number. And then I'm also going to switch the first 2 rows. So I'm going to end up with like 2, 2, 3, 0, 2, 1, 0, 0, 0. Something like that. Okay? Okay, roughly it's in row echelon form. Okay? So now I could put z equal to t if I wanted. Okay? Or would you guys prefer that I divide through by 2?
No, I don't. I like using z as 2t.
Okay, I don't really like to use z equal to 2t because I've never done that before. So I want to be consistent how I always do these problems. I think maybe what it would be better is, let me just do this. Let me go ahead. It is going to introduce fractions, but not in a bad way, right? So if I just divide through by 2, you don't have to do this, but I just think it's going to be a little bit cleaner. So let's just do that. That wasn't that big of an extra step, right? So just divide through by 2 so that we get our pivots equal to 1. I really would rather, I mean, Frank, it's not wrong to let z equal 2t. You could make that work for you, but it's just not the way I've done the problems. I'd like to be consistent with my approach. So I'm going to use z equal to t. Now, if z is equal to t, then can anybody tell me what will y equal?
Negative 1/2 t.
Very good. Negative 1/2 t for y. Okay. And now I got to go back to the first line. I might actually want to write this one out. So the first line, this is x plus y. Well, y was negative 1/2 t. And then plus 3/2 of t has to cancel to 0, right? So this actually is x plus t equals 0.
Yeah.
3/2 minus 1/2. So that's x plus t. So then x would be equal to what?
Negative t.
Negative t. Great. So can somebody give me an eigenvector that we could write down for this particular eigenspace?
Negative 1, negative 1/2, and 1.
Negative 1, negative 1/2, and 1, right? That's after you bust out the t. Okay, bust out the t, that's what you're going to get. All right, so we have that one. Oh, and then of course I can write down my first solution. My first solution, my x1 of t. What is it going to be?
E to the negative t.
E to the negative lambda times t, so
Yeah.
negative t, times what?
The
vector that we just wrote down, exactly. So negative 1, negative 1/2, and 1. Okay, so let's just put that in a box so we don't lose track of it. That's my first solution. Okay. Now we're going to go on to the complex eigenvalues. Okay. So the next lambda is going to be 1 plus 2i. All right, so I have to find the null space again. And it's a 3 by 3, of course. And what I'm going to do here is subtract 1 plus 2i from the main diagonal. So what's that going to give me? It's going to give me
negative 2.
Negative 2
minus
minus 2i. And then negative 4 and negative 2. This is looking pretty ugly. And then the second row, we're going to have negative 4. And then I'm subtracting 1 plus 2i, so it's going to be negative 6 minus 2i. And then negative 6. And then on the third row, I have 4 and 8. And then I take 7 and I subtract 1 plus 2i. It's going to be 6 minus 2i. So there it is,
Yeah.
in all of its ugliness. Okay, this is the null space. Now, again, I know I have to be able to cross off a row. Okay, so I have to be able to cross off some row. So, anybody have a preference which row they cross off? See, I actually would like to cross off the first row, just because the negative 4 and 4, I'll be able to leverage against each other and make a 0 out of that pretty easily by adding the two together. So let me just cross off the first row. You don't absolutely have to do that, but I'm just trying to make it as easy as I can. All right? So we have that, and then what I'll do after I've done that is I will take this, well, first of all, I'm going to move the row that I crossed off as a row of zeros at the bottom. And then I'm going to take the middle row, I guess I'll put that up at the top now. So negative 4, negative 6 minus 2i, and negative 6, just put it at the top of the matrix. And then I'm going to add the second row to the third row and put it in the middle there. So negative 4 plus 4 is 0. And then I add this negative 6 minus 2i to 8, and I get 2 minus 2i. And then when I add negative 6 to 6 minus 2i, I just get negative 2i. Make sense so far?
Mm-hmm.
Okay, here's what I'm going to recommend that you do. Instead of just establishing z as a free variable and then having to solve for y, you can see why solving for y will not be any fun. The second row reads like that. To solve for y, I would have to divide by 2 minus 2i, and that means you're getting fractions with complex numbers in them. Those are very hard to simplify. It's not that you can't do it, but it's just messy. So I'm going to give you a better approach here. Okay, what I would suggest that you do, guys, is in this middle row, you play the trick that I've used before with two variables. Notice there's no x on the second row. So I only have a y and a z, and I'm trying to cancel out those two variables. So you remember my trick?
Yeah.
You switch the positions of those two numbers when you write down y and z, and then you change the sign of one of them. Okay, so this is that trick. Let me just make sure everybody remember when we had things like there's a row with an a and a b in it. Then we made a vector out of it where we put the b first and then the a, and we swapped the sign of one of them. That way the dot product would be 0. That's how we got a vector that was in the null space. Okay, so I'm going to do that right here with this second and third entry. So I'm going to put the negative 2i first, and then the 2 minus 2i, and I'm going to change the sign of negative 2i to positive 2i.
Mm-hmm.
Okay? Are we all right with that?
Yeah.
Okay, great. So that's just with y and z. I haven't figured out what x is yet, but y and z, just from the second row, I'm just swapping these two and changing the sign of one of them. Clear enough? Now I got to go back and find x. In order to do that, I really do need to write down the first equation. So the first equation is negative 4x, and then plus negative 6 minus 2i times y, which was 2i, and then minus 6 times 2 minus 2i, which was z. All of that has to be 0. That has to all be 0. Okay. Well, I'm going to try to simplify this a little bit. So I have negative 4x. Negative 6 and 2i is actually negative 12i. Right? And then 2 times 2 is 4. There's a minus sign here, but there's also an I squared. Remember that I squared is equal to negative 1. So I actually have a double, so that negative 1 cancels this minus and makes it a plus 4. Okay, and then what do I have over here? Well, I have a minus 12. And then I have a double negative again, so it becomes a plus 12i equals 0. The 12i and the minus 12i cancel. And I actually now can, 4 minus 12 is negative 8, and I can put the 4x on the other side of the equation. So x at the end of this calculation finally is negative 2. Okay, x is negative 2.
How did you cancel the i's to get just a 4?
So I squared is just negative 1.
Okay.
And it's being multiplied by 4, so that's negative 4, but it's being subtracted, so that's why I wrote it as positive. Make sense? Everybody else okay so far? Okay, great. So I can actually write down this vector as well. So this vector v would be negative 2, and then 2i, and then 2 minus 2i. You might notice that there's a factor of 2 sitting everywhere there.
Mm-hmm.
If I take it out, if I divide it through by 2, am I wrong?
No.
No, because any multiple of an eigenvector is just another appropriate eigenvector. So I'm allowed to use whatever eigenvector I want. So it's no problem, but I'm not required to take it out. I can leave it if I want to. Let me just leave it. I think in the solution I actually did take it out, so there's no factors of 2. We can leave it here. It's not a problem. So then we're going to get a solution, x of t, that looks like e to the 1 plus 2i times t, and then times this vector that I just calculated a moment ago, right there, like that. Yeah, Bill?
For x, y, and z, are they all multiplied by t?
They are essentially multiplied by t as well, but again, I'm just like busting it out and getting rid of it. So there's no reason that you have to write that down. Okay? Great, so this is what we end up with. Now, what we have to do here is rewrite everything in terms of sines and cosines. So the e to the 1 times t, that's just e to the t. And then I have cosine of 2t plus I times sine of 2t. So everybody needs to make sure they know that Euler formula really well. All right, and then on the vector part, remember that what we have to do is split it into basically the real piece of it. So everything that doesn't have I on it. So there's a negative 2 in the first entry. The second entry doesn't have any real part, so 0. And then the third entry has a 2 on it. Okay, we have that, and then plus I times, well, now we have to see what I is multiplied by. Nothing on the first entry, 2 on the second entry, and negative 2 on the third entry. We get that. Okay? And now what we're going to do is just FOIL that out. All right, cameraman's doing his job here. So we're going to FOIL this thing out. And I have the e to the t out in front of everything. And then when we FOIL this out, of course, I refer to it as FLOY. So I'm going to do the first part where I take cosine of 2t times the vector negative 2, 0, 2. And then the last part, now guys, on I times I get I squared, which is minus 1. So there's a sign change, a minus sign. Sine of 2t times the vector 0, 2, negative 2. Okay, get that? And then, so that's like the F and the L, the firsts and the lasts of the FOIL. And then I have to do the outers and inners. The outers and inners will have the I on it. Okay? So the outers is going to be what? Cosine of 2t.
Times
0, 2, negative 2. Very good. Okay, that's the outer part. And then for the inner part, what will we have?
plus sine of 2t times
Sine of 2t times?
yeah, negative 2, 0, 2.
Negative 2, 0, and 2. Exactly. So there it is. Okay? Now, this, so there's your FLOY for you. Now, this is a good example of where I did something in the class notes where I showed a bunch of steps you don't really have to do every single time, because what I did next, if you go back to the class notes, is I went back to the other lambda, the 1 minus 2i, and then I worked it all out in detail as well. And then I realized, oh, well, if I take this solution and I subtract it from the solution I get for the other lambda, then I can extract a real solution from it. And then I can also add them. I think you have to divide by 2 or divide by 2i or something like that. But all of that stuff you guys don't have to do, because I was just showing you in the notes so you could believe me that I can get real solutions out of this. But what I want you guys to do now is to just remember that this part right here by itself will form a real solution. And then this part by itself will form a real solution. So I'm getting, with this lambda alone, I'm actually getting both of the solutions for the 1 plus or minus 2i. So I'm going to go ahead and write them down right now. x2 of t and x3 of t. So is everybody following what I'm saying? You don't have to work out the other lambda. I did it in class on the first example, but you don't have to do that every time. So this is just going to be e to the t times cosine of 2t times negative 2, 0, 2, minus sine of 2t times 0, 2, negative 2. Okay, so that's just the first part. That's really coming from the f and the L of the FOIL that we have. And then the second solution, we also have e to the t, and which is really the third solution, I should say. We have cosine of 2t times 0, 2, negative 2, and then plus sine of 2t times negative 2 and 0 and 2. Okay? So there you go. As long as you put things in boxes and make it easy for me to find and read, I'll be okay with you guys just on the last step. Because it's not the final answer yet. We have to still put down the general solution. What would I want to write down for the general solution here?
C1.
C1.
X1.
X1 of t, good. Plus
C2, X2,
C2, X2 of t,
C3, X3.
plus C3, X3 of t. Exactly. Okay, and you can just say that where above. Now, if you're going to do that, guys, be careful. Make sure you did tell me what X1, X2, and X3 are. If you were sloppy and you didn't label things properly, then this is not going to be a good answer. But as long as I can go back and find X1, X2, and X3 above, I'll be okay with that. Make some sense?
Yeah.
Are you okay with that? Okay, super. It's not really fair for me to ask you a phase portrait question here because it's a 3x3 matrix. But let me just imagine, suppose that we only have these lambdas right here, 1 plus or minus 2i. Can you tell me if it was just those two eigenvalues, 1 plus or minus 2i, would we have a saddle, a sink, a source, a stable spiral, an unstable spiral, or a circle? Unstable spiral. It's so easy to answer that because you just have to look at the lambda. If they are complex numbers, then you know, of course, you can see the sines and cosines. You really just look at this part of it, right? You see the sines and cosines, which rotate every 2 pi units back to wherever they started. And these e to the t's are what make the radius of those circles get large. As time goes on, the solutions are drifting farther and farther away, stretching farther from the origin. So this would be an unstable spiral if it was just this 2x2 problem. Because it's a 3x3, I can't really ask you that question. This is a little bit more convoluted to actually describe what it would be. But I just wanted to kind of go over that. Okay, excellent. Anybody have any questions or issues with that one? This one?
So, would you ask us to solve for the particular solution and give us like an initial value?
Yeah, I could give you an initial value here, and then you'd have to find C1, C2, and C3. I'm going to actually do that on the next problem.
Oh.
Yeah, so there could be a follow-up, a second part to it where I ask you for that, but I don't think I'll ask it on this problem. Okay, everybody so far so good?
Yeah.
Okay, now I want to do another example. I'm doing kind of the longer problems first, because that way we can cruise through the other ones later on when we're not quite as fresh.
Another quick question.
Go ahead.
Can you show us how to make that into a matrix of solutions again?
Oh, how to rewrite this?
Yeah.
Yeah, sorry, Luis, I'm going to make you
Nice.
over here for a second. So basically, what you do, so you want to put this like into a single, it's not really a matrix, it's a compressed vector form, right? So you have sort of 3 rows. There's the top row, the middle row, and the bottom row.
Mhm.
If I just read across the top, so if I just read across, like I'll just circle what I'm talking about here. If I read across, it's a bad circle, but if I just read across the top, I can see what I have. So negative 2 times cosine of 2t, and then minus nothing.
Yeah.
All right, and then on the middle row, I have nothing minus 2 sine of 2t. And on the bottom, I have 2 cosine of 2t, and this is a double negative here,
Yeah.
so it would become plus 2 times the sine of 2t. That make sense?
Yeah.
Now, I'm not really, it's hard for me to ask you a question where I say, you must give it to me in this form. I mean, there wouldn't necessarily be a reason you'd have to do this, but yeah, that's the way it would look. Okay, great. All right, now I'm going to come over here, and we're going to do problem 4 on the review sheet. So solve x prime equals ax. A is equal to -2, -1, 4, and 0, -1, 0, and -1, -3, 2. And this time, there's an initial condition, x of 0 is equal to -2, 1, 1. Okay. 3 by 3 is kind of my favorite size to work with. It's not so small that it's trivial, but it's not unmanageable either. So 3 by 3 is a good size to practice a lot of problems with. Notice I'm not giving you the lambdas. If I don't give you the lambdas, it must mean that they are not too hard to get on your own. So you should be prepared to come up with those. So let's try and do it here. I'm actually going to have to do the whole characteristic equation calculation, right? So for the solution, I have to take the determinant of, I'm going to subtract lambda from the main diagonal of the matrix. So this is going to be the form of it, like that. Subtracting lambda from the main diagonal. And now the all-important question. Do I want to use the arrow method to find that determinant?
Nope.
Oh, heck no. Not at all. Right? What would I rather do?
Go back to
Expand, and what do I want to expand?
row 2.
Second row. Second row. Look for the zeros, guys. You gotta, if you pick the wrong row or column, it'll be so much harder. So we're going to pick the second row. -1 minus lambda is right here. And then I cross off that row and column, and I have just the determinant of the 4 numbers on the outside corners, right? So that's going to be -2 minus lambda times 2 minus lambda plus 4. Okay, it's really important that you do this part carefully because you want to get these lambdas right. Okay? All right, good. And now, do I want to multiply the whole thing out?
No, because it ends up.
If you did that, you'd end up with a cubic and you'd have to factor the thing again, right? So let's leave it with the -1 minus lambda on the outside. The part that's in the brackets, if I multiply just that part out, will only be a quadratic. And I can deal with a quadratic, right? So I'm going to take the part that's in the brackets and I am going to expand that out. So notice I have 2 lambdas here, so lambda squared. Okay, and then I have a +2 lambda and a -2 lambda, cancels. And then I have a -4 and a +4 that also cancels. So it's actually just that. Okay, great. So lambda, my lambdas are, what are my lambdas?
0, 0,
Yeah, 0, 0, 1.
and 1.
Or negative.
Okay. Whatever is being subtracted from this number has to be, the lambda is the same number again. So it's -1. Okay, guys, it's worth taking a second chance just to make sure you have that right. First of all, these 3 lambdas have to add up to the trace. If you check that, you might catch a mistake. Like if you accidentally wrote 1 here instead of -1, you would catch that. That would be great if you did. So it has to be -1. And also, yeah, it's just -1 minus the same number is what is going to give you 0. So the lambda needs to be -1. Okay, so we have no complex numbers this time, but we do have a repeated eigenvalue. Does that mean the matrix is defective? Not necessarily, right? It might be. Let's go ahead and, well, which eigenvalue do you want to work on first?
The 0.
The 0, because it's the repeated one, okay? So let's do that. So let's do lambda equals 0. This means I need to find the null space of... Oh, I have another question for you before we go any further. Go back to the original matrix real quick. This is just a side question. Is this matrix going to be invertible?
No,
Why not?
because one of the lambdas are 0. So
Like,
that would be
remember, when you multiply the lambdas, you get the
determined.
determinant of the matrix. So if these are your lambdas, then the determinant is 0. It means the matrix is not invertible. Okay, just a little side point, just to kind of keep in mind. Remember, guys, invertible has nothing to do with diagonalizable. I saw a few people on the quiz. I think on the quiz there was also a lambda of 0. And so some people said, a lambda equals 0, therefore the matrix is not diagonalizable. I'm like, no. Lambda equals 0 means that the matrix is not invertible. Okay, but it could still be diagonalizable. We just don't know yet. All right, so let's take the null space of this matrix as we have it here. Okay, so we just, because we're subtracting 0 from the main diagonal. Now here's the thing, guys, if you just, okay, I'm going to do this without doing any EROs at all. Watch how I'm going to do this, because this really makes life easy. Notice that y has to be 0 from the middle equation. Okay? As soon as y is 0, now the first column of the matrix doesn't even matter. Right? The second column of the matrix doesn't even matter. You can just cross it off. That's because it's going to be multiplied by 0. Right?
Mm-hmm.
Okay? So then the x, because the variables are set up like this, right? Correspond to those columns. Just trying to make things easy for you.
Yeah.
So the y column is gone. Now if you just look at x and z, notice that these two rows are multiples of each other. No surprise there. Let me cross one of them off. And now I've got -1 and 2. You know, I can play that swapperoo game even with x and z. I don't think I've ever done that before, but there's no reason why you can't take these two numbers, swap them, and change the sign of one of them. So I'm just going to get 2, 0, 1. Okay? So I did that very fast, right? Without having the chance of really making any mistakes. Does everybody understand that? Because I don't mind repeating it again if it's not clear.
Can you repeat it, please?
Sure. So coming back, I first look at the middle row just because it's the easiest row. In the middle row, we're just saying 0 times x minus 1 times y plus 0 times z equals 0. So that's where I'm getting y equal to 0. Now once y is equal to 0, then, once y is equal to 0, then, for example, the first row, once y is equal to 0, the first row reduces to -2 and 4 for x and z. And the third row, which is -x minus 3y plus 2z equals 0, as soon as y is 0, it just becomes -x plus 2z equals 0. And now those two equations are just multiples of each other. So I'm crossing one off, and now I'm just looking at this and saying, well, what about x and z? I switch the 2 and the -1 and change the sign of one of them. Okay? Is that good? Everybody following that now? You can, of course, go through the whole long process if you want to and do EROs and so on, but that just makes it a little bit faster for you. Okay, so can you tell me yet if this matrix is going to be defective or not?
Yeah.
See, the eigenvalue has a weight of 2, and the eigenvector, we only got one of them, right? So it does not pull its weight. So this is a defective matrix. So we already know now that we are in the situation where we're going to have to use the W's.
Yeah.
Right? This is the stuff we just learned recently. So we're going to have to use the W's on this one. Okay, so let me remind you how that works again. Okay, so of course we have one solution we can write down right now, which is, what would be the first solution that we could write down?
E
to
to the 0.
0, which is just 1,
Yeah.
times v. So actually the first solution is just literally
V.
The vector.
that vector by itself, no time in it at all. There's no time value at all. Okay, the second solution would just be, this is where we have to use the W's.
Yeah.
Okay, so let me remind you what that will look like. So for the second solution here, it's going to be e to the lambda t times w1 plus t times w2. And the trick with the w's, this is really the thing we need to review right now. Here's w1, here's w2, and here is 0. And each hump that I pass over is like multiplying by the matrix A minus lambda I. But in this case, lambda is just 0, so it's really just multiplication by the matrix. Okay? So we need to